Hello, so in this video we are going to discuss the difference between, or at least which algorithm is better, which sorting algorithm is better, and we are going to talk about quicksort and merge sort. So one thing they have both in common is that they are both comparison based sorting algorithm. So what does that mean? That means that the only operation they use to sort the input is comparison, checking if it's less, if two numbers, one of them is less than the other, is bigger or is equal. So that's the only operation they use. And these algorithms are known that they have, that they can't have a better complexity than overlagen on the average case. You can't have a comparison-based sorting algorithm that do better than this complexity here in the average case. So they have that in common. So we know that in the average case, they are both overlagen. But, so let's look at their complexity in both the average case and the worst case. So merge sort is both overlagen in both its worst case and its average case. But quicksort can degenerate and in its worst case can become so in its worst case can be Oven squared. But still in its average case is overlagen. So we might think that because of this, quicksort is better. Merge sort is better, since even in the worst case, we will still get overlagen. So is this true? But before that, let's just see explain why is quicksort Oven squared in the worst case. So quicksort chooses a pivot to do the sorting. Okay. So if you have an array where you choose the first element as the pivot, which is the one that you are compare with, and like arrange the element smaller than it to the left or to the right, and bigger than it to the right. So an already sorted case, if you have an array that is already sorted and you choose the pivot as the first element, then this right there would make the sorting becomes Oven squared. If also you have for the same reason as this, if you have an array that is also already sorted and then you choose the last element as the pivot, in that case also we get Oven squared. So some people try to implement quicksort by choosing the middle element as the pivot, but even in this case you can still find exploit this and find some input that would make quicksort degenerate into Oven squared. So basically the worst case being Oven squared depends on the choice of the pivot, and also only for some cases of the input. So for example, when we choose the first element, if the array is as the pivot, if the array is almost sorted or already sorted, then in that case quicksort degenerates to Oven squared. Okay, so I now have two implementations, one of merge sort and the other of quicksort in Python, just to get a concrete idea of how both works. So both merge sort and quicksort just can check the first special case, which is if the list is less than, the length of the list is less than or equal to one element. It just sorted by default, so we can just return it. The other part is for merge sort. So merge sort, we just split it in half. We take the left part and the right part we call merge recursively on both, and then we merge everything together. So that's what we are doing here. We take the middle element or the middle index. We put in left everything to the left of that middle index, and to the right everything to the right of that index. And then we recursively call merge sort on the left side, and recursively call merge sort on the right side. And after that, we just merge the two together. And here we take advantage of a method in heapq library, standard library, that already does the merge of multiple sorted input. And so we just take advantage of that and merge our both left and right. So that's a merge sort. Quicksort first picks a pivot, which here we pick the first element as the pivot. We could have picked anything else. We could have picked the last element, the middle element. Depending on the strategy, you get a different case of a worst case input. And so we pick each element of the array, we check if it's less than the pivot, then we add it to the less list that we defined here. If it's bigger than the pivot, we add it to the more list. And if it's equal to the pivot, which is this else here, we put it in the pivot list, which is all elements that are equal to the pivot. And then we recursively called quicksort on the less part of the list, and we call it also recursively on the more part. And then after that, we will have less sorted, more sorted, and then we have pivot list, and so we just concatenate the three lists together, and that's essentially it. Next, we'll take a look at just how they are really different, and is one better than the other. So, just to keep comparing them, I showed the version in Python. Let's see in Java. So for the merge sort here, I have a similar one, almost the same one. We just pick the middle, and then we do merge sort recursively on the left half and then on the right half, and then we merge the two. And here we are just using our own merge function, which is pretty straightforward. It just compares and see where the elements fits and put it in the position that it should be in. However, the quicksort version that I have here is an in-place version, and yeah, I wanted to explicitly have this example because I have the other one that is similar to the Python one that creates lists, but I prefer to explain here the in-place version. It's often the most used one for quicksort, so it just picks it partitions the list according to a pivot. So while the element is less than the pivot, it puts it so while if the element is less than the pivot, then it goes to the left and swaps it. If it's to put it to the left, if it's bigger, puts it to the right. And we have this swap function that swaps them, and we recursively call it on the left side and on the right side. And that's basically it. And once we have exceeded f, our pointer f is bigger than L, it means we are done. We finished processing the list. So let's see what are the advantage of this here. What is the advantage of this version of Quicksort? So the main advantage of the version of Quicksort that we just saw that does sorting in place is something called so it's because of cache locality. Let's see what that is. So what we talked about before is that often sorting algorithms complexity refers to the number of comparisons that we do between the elements, and the number of swaps that we do if we are sorting in place, if we are sorting an array in place, comparing the number of swaps. But this is actually a good measure of performance, especially it's independent of the hardware we are doing the sorting on, so that's good. But there are other things that really in practice come into play here. One of them is locality of the reference. And so what is locality of preference? It's basically, do we read a lot of elements which are probably in the cache or not? So this plays also an important role in determining the speed of the sorting algorithm. So in this case, Quicksort actually has better locality of preference. It requires a little additional space, and it exhibits very good cache locality, and this makes it in a way faster than merge sort in some cases, or in many cases, let's say. And this can be seen, so in the inner loop that we saw of Quicksort, it compares several values in the array with the pivot element that we have chosen. So you would have the pivot, and you compare all other elements against it in the same array. So in other words, Quicksort does, however, for merge sort, you compare every you compare both terms. Are basically here one term is fixed, and the other terms change, and then you compare each of them with the pivot. For merge sort, the both terms are different for each comparison that we do during the sorting. So in other words, Quicksort does basically half as many reads as merge sort. And on modern CPU, performance is really dominated by access times, and so since in merge sort every time we do a comparison we access two elements, compared to Quicksort where we access just one element, that makes Quicksort wins in this case. And and so merge sort needs just much more memory and RAM accesses, since every accessory array we create for merge sort is accessing the RAM again. And yeah, that's basically why in some cases Quicksort can be faster in practice. Now, Quicksort, as we said earlier, Quicksort definitely has the complexity on squared in the worst case, but there are a lot of ways to avoid this. For example, there is a version of a sorting algorithm called intro sort, which keeps track of the recursion depth that Quicksort is doing, and basically switches to an algorithm like heap sort. So switches to heap sort if it notices that Quicksort will degenerate, and so in a way avoiding the O(n) squared worst case scenario. So basically with this version in Quicksort, it guarantees the overlagging worst case behavior with low memory overhead and with maximizing the benefits of Quicksort that we talked about earlier. So it makes it better than merge sort. There is also another variant that can make Quicksort better, which is randomized Quicksort. So randomized Quicksort, basically choosing, kind of, if we try to simplify it, is choosing the pivot randomly. While it still has O(n) squared total worst case complexity, it doesn't completely eliminate it, but it makes it happen with a vanishingly small probability. And so in a way that's also better. So it makes it very low. It makes the probability of the worst case occurring very, very low. And so with this we can get the cache locality benefits that we talked about earlier. And I just wanted to point you to something called cache oblivious algorithms, if you want to kind of explore more the space of algorithms that explore cache locality. And yeah, I think it's a good subject to to look into. Cache oblivious algorithms. Basically, it's algorithms that take advantage of the cache. However, with all of this being said, there is still a case where merge sort can be a better option. And this case is if we need, so we know from what we saw that merge sort needs a lot of auxiliary memory in order to like separate the list into different lists and then merge them later. But if we have a huge amount of data, so if you have a huge set of data to sort, then merge sort is kind of one of the most used sorting algorithms because there is a variant of this called external sorting that we can use merge sort with. So yeah, look into that, and that's one of the cases that merge sort can be really useful. Yeah, and that's all for this video. See you next. Bye bye.